Hey, what's up everyone? Professor Wolverine here, and I'm here to bring to your attention a major issue in the mathematical world.
Time to get swifty in here.
What is the correct ordering of the theorems in the fundamental theorem of calculus? Okay, so this is my ordering. This is what I call part 1, and this is what I call part 2. Part 1 is about antiderivatives, and part 2 is about computing Riemann integrals. Okay, so different people order them differently. Some people call the first part the second part, and the second part the first part, and it makes it very confusing because it just makes the numbering impossible to use. If you say by the first part of the fundamental theorem of calculus, and the person you're talking to says, what do you mean by that? It's like, what is the point of having an order?
Order! Order!
Chaos, disorder, disarray, disorganization, confusion, mayhem, bedlam, pandemonium, madness, havoc.
Madness. This is Sparta!
Turmoil and commotion.
X-axis?
Yes.
Right there?
There's the x-axis. Why don't you explain this to me like I'm 5?
Okay, I'm not going to explain it to you like you're 5. Look, if you're 5, what are you doing here? Go watch some cartoons. Seriously, you're going to find this very boring. Look, you pretentious little shit, get the out of here. What the hell are you doing? You son of a...
Look, if you're 5 and you understood anything I just said, tell your parents to contact me immediately. We need to talk.
Okay, for example, let's look on Wikipedia. Wikipedia clearly states the first part to be the same as what I said, and the second part to also be the same as what I consider to be the second part. Whereas this person right here, D. Joyce, does the opposite. Joyce says that Theorem 1 is what Wikipedia calls Theorem 2, and Theorem 2 is what Wikipedia calls Theorem 1. Now, the reason they're doing this seems to be because of what some person named Orisme did back in 1350. But I don't really know about this. I don't really know. I'm not convinced. So Joyce is saying that because of what Orisme wrote in 1350, that Wikipedia is getting the history backwards. I've looked a bit about what Orisme wrote, and I'm not convinced that this justifies what Joyce is saying. Okay, so I'm basically going to give you 2 arguments for what is the correct ordering of the fundamental theorem of calculus. The first argument will be from a historical perspective, and the second argument will be from a mathematical perspective. Which one mathematically is more natural to call the first, and which one is more natural to call the second. Okay, so when doing this kind of thing, it's a bit confusing because you have to decide how far back you want to go. But I would say that it's most natural to go back to the time of Sir Isaac Newton. So maybe you're a Leibniz person, but if you are, go f yourself. No, I'm just kidding. I'm just kidding. Nothing against him. But I just didn't find anything about if he said anything about this issue. So this paper is called Historical Reflections on Teaching the Fundamental Theorem of Integral Calculus. It's by David M. Pursued, and if you want, you could take a look at it. Now let's go to what Newton has to say on page 104. So Newton had worked out his ideas of calculus in Lincolnshire during the plague years of 1665 to 1666. So Newton invented calculus during the plague. What did you do during COVID? What did you do? During COVID, I started the YouTube channel explaining what Newton did during the plague years. I also grew a beard and started another YouTube channel about beards. I'm also in the process of editing a paper which I'm planning on publishing this month. So, crossing my fingers. So that's sort of like what Newton did, right? Okay, fuck you, okay? Fuck you. What did you do something better? Did you? Probably not. What did you do? You watched Queen's Gambit? Is that what you did? You think you're so cool because you watched Queen's Gambit? What, you watched Wonder Woman? You watched Tenet? Does that make you cool? Is that productive? What you did like 2 push-ups probably during the whole COVID? Is that it?
The floor is disgusting.
Can someone please help me?
You went on Instagram, you're watching my freaking YouTube video? Why are you even watching this? How is this important? How is this important? So basically the point is, in problem 5, he asks to find the nature of the crooked line whose area is expressed by any given equation. In other words, this is asking, if we have an expression for the area under a curve as a function y of the, however you pronounce this word, Old English, then how do we find the equation of the bounding curve? This is the antiderivative part of the fundamental theorem of integral calculus. The rate of change of the area is given by the ordinate of the bounding curve. They use the word ordinate for derivative. Anyway, now let's go a little further. Now the evaluation part of the fundamental theorem of integral calculus appears in problem 7. Okay, and as far as I know, 7 is bigger than 5, so problem 7 came after problem 5, alright? Which means that whatever theorem is stated in problem 7 should be number 2, and this is where Newton states the evaluation part of the fundamental theorem of integral calculus. That is, how to compute the Riemann integral from a to b of a given function.
If you look at the same paper, you will find that many other established mathematicians agree with me, including Cauchy, Hardy, and Courant.
Okay, so I have two arguments that from the mathematical perspective, the ordering I gave is the correct ordering. And I have no arguments against it. And I'm not biased, I just haven't found any. I don't have a dog in this game, I don't care. Okay, so from a mathematical perspective, in order to state the fundamental theorem of calculus, both parts, you need to know about derivatives. Now, once you learn about derivatives, from a mathematician's perspective, probably the most natural question you could ask is which functions have antiderivatives? And that's exactly what the first fundamental theorem of calculus tells you. Now what else? Now what's the argument? Now what I call the first part actually implies the second part for all continuous functions, which are pretty much all functions you would see in a calculus course. And from a historical perspective, it's pretty much all functions that they considered up until like the 19th or 20th century. Let me show you. Well, let's let this be denoted by f of x. So then, clearly, f of b minus f of a is equal to the Riemann integral from a to b of little f. Right?
Affirmative.
But from the first part of the fundamental theorem of calculus, this f right here is an antiderivative of little f. And since all other antiderivatives differ from this big F right here by a constant, which is going to cancel out when you take the difference, you get that this is true for all antiderivatives big F of little f, which is basically the second part of the fundamental theorem of calculus.
Do you see it now? Or should we finish this on the board?
Okay, of course, you need to assume some continuity on your little f in order to prove the second part of the fundamental theorem of calculus using the first part. But basically all functions you would be integrating in a calculus course are continuous anyway. So it makes more sense to call the first part, and the second part, the second part. Now you might be asking, well, doesn't the second part imply the first part? Well, no, it doesn't. Now you might think that the second part of the fundamental theorem of calculus, or what I call the second part, implies the first part, because you could take this, so this is the second part of the fundamental theorem of calculus, and you could divide it by b minus a. And then you could take the limit as b goes to a. So here we're going to take the limit as b goes to a, and here we are also going to take the limit as b goes to a. And right here, on this side, you'll get f prime of a. And on this side, you get, well, whatever the derivative of this is, right? But f prime of a is just equal to f of a. So you might say, oh, well, look, we deduced the first part of the fundamental theorem of calculus from the second part of the fundamental theorem of calculus, because this right here is saying that if we differentiate this integral, we get little f. But this doesn't actually work. Why? Think about it.
No, God! No, God, please, no! 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 No!
In order to use this argument, we had to assume first that the function for which we were integrating had an antiderivative in the first place, which we don't know that it does if we don't use the first fundamental theorem of calculus.
Also, from the perspective of importance, while the second part of the fundamental theorem of calculus is definitely important, I would argue that the first part is at least just as important, maybe more. It's crucial to solving differential equations. Don't believe me? Check out the Picard-Lindlof theorem. Okay, so let me summarize my argument. From a historical perspective, my ordering is the correct one. And for the mathematical part, since what I call the first part of the fundamental theorem of calculus essentially implies the second part, but since the second part doesn't imply the first part is more fundamental, and it makes sense to label it as Theorem 1. Okay, so I'm Professor Wolverine. Thank you for watching. Please like, subscribe, share, and comment. Hit the notification bell. I respond to all comments. If you have any questions, including math questions or physics questions or questions about anything else, let me know, please. Again, please share this video to anyone who you think might find it interesting. I'm taking suggestions for videos, so if you have any requests, please let me know. Until next time, I'm Professor Wolverine, out. Thank you. Oh yeah, also let me know, do you agree with me, do you disagree with me, why and why not? Let me know in the comments. If you could provide any interesting evidence, let me know. What did Leibniz think? Who knows? What do you think? What do your instructors think? Let me know.
Booyakasha!
Booyakasha!